So let me go on with quantum information. So first of all, I'd like to thank the organizer for having organized this event. I think it's very good to be together. I've also learned a lot about this, the history of this institute. Admittedly, I did not know much so far, and well, I'm very impressed by, you know, the history of this institute and by the track record of people who actually built it and are still working there. So thanks a lot for this. I'm going to talk about quantum information, so I'm simply like the representative of a group now, a new group which you know, started like 3 years ago, and that we had together with Jean-Daniel Bancal. The group is getting more and more students and postdocs thanks to the hype, I would say, around quantum technology. So we take benefit from that to get money from the European Commission and from the French Quantum Initiative. And again, what I'm going to present you is some work that we do in this group. Don't believe that this is only my work, but this is the work of the entire group. So the title is The Quantum Threat to Communication Security, and the talk will be mostly about quantum computing and slightly about quantum cryptography. So the question, so it has still to do about, it's still related to quantum cryptography, and an important question in quantum cryptography is how to transfer data safely. So the kind of data that we consider are like health data or diplomatic data, you know, the kind of data which is very sensitive and remains very sensitive for a very long period of time. And the question is, how do you transfer this kind of data in between two locations? If you want to do that, you can use classical techniques, classical crypto systems that are called RSA or elliptic curve. And the security of this classical crypto systems rely on computational assumptions. So let me give you an example. RSA, for example, is based on the factorization problem. This is a problem that is kind of simple to explain. You can see it as a game where I take two prime numbers, I multiply them together, I give you the result, and you win the game if you give me back the two prime numbers that I choose initially. So this seems very simple, but it turns out that there is no known classical algorithm that can solve this problem efficiently. And based on these assumptions, you know, you build up a crypto systems for which, again, the security is based on the assumption that there is no known algorithm for solving the factorization problem. And we won't be able to find an algorithm to solve that particular problem in the coming years. Well, it turns out that if you get access to a quantum computer, you can actually solve the factorization very efficiently, and therefore you can hack RSA crypto systems. So how does a quantum computer works? Well, it works to some extent in a quite similar way than a classical computer works, in the sense that in classical computing we have bits, and in quantum computing we have quantum bits or qubits. These are simply two-level systems, like, for example, it can be the energy state of a single atom, and you simply label 0 and 1 the two states of your qubits. Now, in a quantum computer, you need a bunch of quantum bits. So I'm only representing here 3 qubits, but keep in mind that in a quantum computer we need much more. And then you encode integers exactly in the way we encode integers in a classical computer. So we simply take, you know, the binary representation of an integer and then encode 0, for example, in the binary form. So you simply encode 0 by putting your 3 qubits in state 0, 1 in putting only the first one in state 1, and so on and so forth. Okay. Now, as in classical computer, you can make operations on these bits, on these qubits, for example, by playing with lasers or microwave fields. And you do have operations that are essentially the same as the one that we have in classical computing. However, thanks to the superposition principle, we also do have access to operations having no classical equivalence. For example, here is what is called an Hadamard gate, or an Hadamard operation. And this Hadamard operation takes, the two logical states and gives two superposition states. So obviously, this kind of operation cannot be implemented on a classical machine, and this lets you believe that you can probably get something out of this quantum machine from which you have operation that cannot be implemented on a classical machine. So let me show you a bit more in detail how we can use indeed this kind of typically quantum operation, or more precisely, how we can try to program a quantum computer. So we do it here at the very low level. So we are very closely, very close to the hardware. And each line here do represent the operation that you do on qubits. So here are the operation that we do on the first qubit, on the second qubit, and so on and so far. So in some sense, times go on from left to right. So you see that initially we have 3 qubits. They are prepared in state 0. And then at the first time step, you apply an Hadamard operation on each qubit. The result, as we were saying before, is now all the qubits are in a superposition state. And if you develop the state, you end up with this superposition, meaning that in one time step, you succeeded to prepare your quantum register in a superposition of all possible integer between 0 and 7. Now let's go on. And let's see how we can efficiently do a computation of an exponentiation, for example. So I'm here considering, a function that I call f, which takes x as inputs and outputs j at the power x. Now, if you, again, write down x in a binary form, you realize that you can compute j at the power x by simply computing a product. And this product is exactly the one that we do here. So we prepare, an other register that is initialized in, the value 1. And then we apply successive multiplication on this register conditioned on the value of the bits of the first register. So what we do exactly here is that, we have created a register encoding x, and a second register encoding fx. And since the first register was prepared in a superposition of all possible integer between 0 and 7, we get in a single step all possible value of fx, or say fx for all possible value of x in between 0 and 7, again on a single step. So this is the kind of parallelization that you get from a quantum computer. And now let me proceed step by step and show you how we can now get, for example, access to some characteristic of the function that we were encoding in the second register. For example, the period of the exponentiation. So this takes the equivalence of the classical Fourier transform, but in the quantum setting. So I'm here in the first line reminding the definition of the classical Fourier transform. I take a sequence of complex numbers, and when I Fourier transform it, I get another sequence of complex numbers where each component is now the Fourier component. And we use this classical definition in the quantum setting by saying if I get a register that encodes all possible value between 0 and n-1 in a superposition with weights that are given by this complex coefficient, I simply use the Fourier transform to get a new superposition, or superposition of the same integer but with a new weights that are indeed given by the Fourier component. Now let me quickly do a fairly simple calculation starting from the state that we succeeded to prepare in the previous slide. So this was a state where the first register was encoding the value x and the second register was encoding fx. Again in a superposition. And now what we do is that we Fourier transform the first register, And if you do that, you realize that these Fourier transform essentially change the weights of this superposition with property that essentially depends on the period of your function. So this means that if you measure the first register, you will be able to access the period of your function. So hopefully with this brief description of the quantum circuit that I was given before, you can eventually convince yourself quite quickly that with this circuit, we do implement the Fourier transform that we had before. We have 3 qubits encoding an integer in a binary form, I, j, k, and the definition that I gave you before, you can check that if you apply it to this particular state, you get a superposition state with particular phases. And this is actually what does this circuit, where you have the 3 qubits. You do apply the famous Hadamard that we saw before to get the superposition state, and then you apply control phase gate to get the right phase in this superposition state. So these does implement the quantum Fourier transform I was describing before, and now we're coming to already an understanding of a complex program that we can implement potentially on a quantum computer, where we have our 2 register. In the first one, we first encode, a superposition of all possible integers, say from 0 to n minus 1. And then on the second register, we compute an exponentiation. And at the end of the day, we Fourier transform the first register and measure the result, which give us exactly the period of this exponentiation. Let me comment on the fact that if you look at the detail on ways to implement a product like this on a quantum register, well, you realize that you can do it with n additions for a register of size n, and for each addition you need n elementary operation. So the complexity of this algorithm goes like n cubed, where n is the number of bits that you have in your quantum register. So the question is, what is it good for? Well, we're now back to the factorization problem that I was mentioning before. And well, these are the steps of a classical algorithm that can solve this factorization problem, but where a step is exactly, this is the hard point classically. The hard point is indeed the point where you need to find the period of this exponentiation. And we have seen before that this can be tackled efficiently with a quantum computer. So we are now arriving at the interesting point where we identify a mathematical problem, the factorization problem, where basically there is no classical solution, there is no classical algorithm that can solve this problem in a polynomial time, but we have a quantum algorithm that can do that in a number of steps that is simply the cube of the number of bits that you need to write and to encode n. Okay, so we say that we have a typical problem where a quantum computer would provide an exponential speed up, an exponential quantum advantage. So this looks good, but now I really want to do that. I'm working in quantum cryptography, so I want to get a computer and hack a classical crypto system because it's going to be beneficial, to sell what we do in quantum cryptography. So what does it actually take? Well, when you look at the detail of currently used RSA crypto system, they use the factorization problem on using integers that takes typically 1,000 bits. So given the scaling of the quantum algorithm, the n cube that I was mentioning before, it means that I'm going to take 1 billion operations to be able to hack currently used RSA crypto system. 1 billion operation means that if I want my algorithm to converge, each operation has to be done very accurately with a precision that goes essentially like 1 over 1 billion, or say 1 over 10 billions. Okay? And if you talk to an experimentalist, they will tell you right away that achieving this precision is simply impossible now, but also in the coming years. So we need to find a solution, and the solution is what is called error correction. So the basic idea is to use redundancy. Instead of encoding a single bit value in a single qubit, we're now going to use multiple qubits to encode a single bit. So for example, in this example here, I'm using 9 qubits to encode a single bit value. So let me show you how error correction work, you know. So I'm here describing an error correction that is called stabilizer code. This is using like a set of independent commuting Pauli operators that I call SI. And from this SI, we define a subspace of the entire Hilbert space, which is simply the state of states that are stabilized by this operator, okay, the eigenstate with eigenvalue 1. And now I'm going, as I was saying before, to encode my bits in this particular subspace. So let me give you an example, for example, on this patch of qubits. So I have 9 qubits, and I'm now defining a specific set of Pauli operators, which are represented by these S operators. For example, in particular, where Si is, you know, a product of Pauli X when I is odd, and is a product of Pauli Z when I is even. So for example, S3 here is a particular product of X operator on the 4 qubit on the top left, and the identity for the rest. Okay, so we have 8 such independent and commuting operator operating on 9 qubits. So these produce a subspace, a stabilized subspace of dimension 2, which I'm going to use again to encode a single bit value. Why is it good? Well, it's good because now that I can encode my bit value in this particular subspace, I can actually measure in practice this particular Pauli products. And if I do that, I know that I'm working in a specific subspace, so that the result of this measurement will always be +1 by definition of the stabilized subspace. Now, if I get an error, the error will put my state out of the stabilized subspace, so that one of this measurement will outcome a -1. Okay, so the game in error correction is simple. You simply take the result of your measurement to identify where errors are, and then you correct those errors. So a hot topic in quantum computing is indeed to provide efficient error correction codes, and this is one of the points I wanted to mention to you, in the sense that to provide good codes, efficient codes, we need to, of course, choose a proper choice of stabilizer. We also need to think about efficient ways to implement the stabilizer. And we also need efficient decoders. So the decoder is the algorithm that we use so that from the result of this measurement, we can identify where the errors are and correct for these errors. And there are many techniques, you know, that are proposed, or are, you know, that colleagues are proposing to build up efficient decoders. So some of them are based on tensor network, for example, other one on neural networks, on reinforcement learning, renormalization group, combinatorial optimization solvers, and so on and so far. And I know that in this room, I have many colleagues who are experts along this line. So don't be surprised if in the coming weeks, in the coming months, I'm come to you, because we're starting a new activity along this line, and I want to know everything about these techniques, all right? Okay, so what do we actually do along this line? 5 minutes, all right. So what do we actually do along this line? Well, we like very much taking algorithm, optimizing algorithm, eventually proposing new algorithm. Think about a platform where they could be implemented, and then find out about the error correction code that is suitable for this particular platform. So the first paper I'm mentioning here is a paper from Google where they showed that with their platform and the error correction code that they have in mind, it would essentially take 20 million qubits to be able to hack RSA crypto systems. And now what we have done is that we thought about a new architecture where we would have access to a quantum memory. So now the way we think about a quantum computer is very closely related to the way classical computer works, in the sense that, you know, we have a large quantum memory that can store essentially all the information, and now we have a very small processor that, you know, process a few qubits at a time. So we take this particular qubit from the memory to the processor, process it, and put it back, and process in this way information step by step, a few qubits at a time. And we show that in this way, this reduces very strongly the requirement on the number of qubits per processor, and basically with 13,000 qubits, we would manage with this architecture to be to hack the RSA crypto system. And finally, and I'm not going to comment on this last work, but I just want to mention that this work has been done with a startup company called Alice and Bob, a French startup company. And what I learned from this paper is that actually extremely good physics, theoretical physics, is nowadays done in startup companies. All right, so we're not yet there. So we don't actually have a quantum computer with 10,000, 100,000, 1 million qubits, not yet. And if you look at the roadmap of IBM, they plan to launch a quantum computer with 1,000 qubits by the end of this year. So we are not yet there, but in the group we are already preparing, you know, to this quantum threat. So we are thinking about new protocol for making cryptography secure, even in a quantum world, even in a world where adversary would have access to quantum computer. This is called quantum key distribution. I have no time to enter into the detail, but well, I can simply tell you that we're now working for years to get provable security, really a security that depends on the mathematical proof and not anymore a security that rely on computational assumptions. And we succeeded, you know, to even reach the point where an experiment was possible, a first experiment showing that indeed we can have access to this new security level, which rely again on the mathematical proof and not on computational assumptions. And this was published last summer, or summer 2022 in Nature. And now one of the aim in the group is to try to build upon this first experiment to improve what we had, what has been done experimentally, you know, increasing the distance, increasing the rates, and so far, and so on and so forth. And this summer, we identify, you know, superconducting qubits as a way to go further ahead, to improve what we already have and reach the point where one day we could eventually have access to this cryptography, a new kind of cryptography where, again, the security rely on a mathematical proof. So something that is secure even against adversary having access to a quantum computer. So the conclusion, the take-home message is that, yes, hopefully I convince you that what we do in the group is fun. And more importantly, if you work in one of these fields and you are potentially interested in working with us, please don't hesitate to talk to us. We would be very happy to share what we know about quantum computing and quantum error correction. Thank you very much.
Questions for Nicolas? Olivier? Do you we have to see? No, you okay. Need to be recorded.
Thanks for the nice talk. the quantum Fourier transform in itself has low rank. I mean, it has low entanglement, about 8, right? It can be represented. So, of course, you described the Shor algorithm, but so can you point out what is the other part which is make it not simulable? Cannot simulate, because if it was just that, it's just not. But
that's right. And furthermore, as you cannot on this representation of the algorithm, the Fourier transform is done at the very end.
Yeah, exactly. So what is the critical?
Yeah, so it's essentially a semi-classical Fourier transform. So the critical part is actually this first part here, where what you actually do, is that you prepare superposition state first in here, and then you do this conditional operation. And the way to write it down is in here, for example. So what you get is actually a deeply entangled state between the two registers, and actually in the RSA or in the Shor algorithm, the size of this register is typically of the size of the integer that you want to solve. So you can prove that the amount of entanglement is huge there.
Okay,
so
this
is a good point in the sense that this is certainly the critical part, if you want to try to simulate these kind of things. But this also can be useful, to witness that indeed a machine enter into the quantum regime. The possibility of simply hacking RSA is a way to prove that there was deeply entangled state in the machine. This is the only way to be able to hack RSA actually. So we can essentially see the algorithm as a way to witness that the machine actually entered into the quantum machine.
Okay, thanks.
Other question for Nicolas. The young people can ask questions as well. Okay. François?
Young people.
Wait.
You mentioned renormalization group. Can you say just a word about it? Where?
No, absolutely not. So please.
Okay, so.
Show me what it is, and I will, at least I can explain you the kind of problem that we want to tackle with these kind of things. But what I can tell you is that people are studying the possibility of using renormalization group to improve the decoder in quantum error correction. So
okay, thank you.
Please come to us and explain us what it is.
I'll do.
It's the right person to come to you. Yeah. So, other questions for Nicolas? Well, if there are not, let's thank Nicolas again. And